second, we have a very easy test. It's like a quiz. It's as short as a quiz. It's not like a test. Maybe you look at your paper and it's solved. It's easy as that. Now, today, I have a surprise for you all. I have a gift for you. This is in my pocket. This is in my pocket. Before we leave, I'm just going to give that to you. I have a very surprising gift for you all. But I'm going to give that to you before we leave. Then please remind me that I give you your present. Now, what we are going to do is that we are going to spend today a little bit easy. And that's the reason I decided to just give that gift to you today. Because we are not just going to give extra lessons. We are going to go some review on the trigonometric functions, Jake, and solve some problems. Because last time that when we talked about this, it was just the short period, and we started it, and we had to finish it right away. Now, Ln of, let's say, today, now we are going to explore some of the very basic techniques we have covered it so far in order to solve something like this. We have a natural logarithm of a tangent of x. Now, you ask yourself, why am I presenting that function to you? What I'm going to do with it? I have to remind you, we are in the calculus course. Now, we are looking for the dynamic moving things. Now, we have to find the rate of change, how this function changes over time. Now, and that's the reason now we are in the calculus class. To analyze the things that they are dynamic, they are not static, the things that change. And that's the reason. Now, before we just move on, I'm just going to remind you of two very important identities that we talked about. So the first one was, we said that d over dx of a function if it is sine of x. We said that we do not prove it, we only accept it. Otherwise, if you want to prove it, you have to just work with that limit to find the derivative. But we accepted that the rate of change of the sign of a variable, when that variable changes, it becomes cosine of that value. And also, we just finished with the second one. We said that d over dx of cosine of the x, which it means that the rate of change of the cosine of the x, when the x changes, it becomes minus of sine of that variable. These two things were incredibly important that when we talked about them, I should say on that very brief period. Now, and also, any questions so far? These things are so easy, huh? That's the thing. You go to the shopping, you go to a grocery store, and they just give you that for free. This is everywhere. You cannot avoid them. Now, also, we set up something different before I just work through that example. We said that imagine that f of x is the function itself. However, we come across some cases that f of x has a baby inside. Then we said that f of g of x. Then we came to talk about that, the chain rule, that day, that we said that in order to find the rate of change of a function, of a composite function, when the variable changes, it's going to be something like this. We said that. Remember the chain rule that we taught? I'm just going to write the results right away. That if you hate writing, for example, the chain rule, connecting these two variables, it's going to be confusing for you. It's going to get confusing for you. Avoid it. Now, I'm going to write the last thing. I said that you get d over d of g of x of f of g of x, which becomes f prime of g of x. You see what happens? Multiplied into a term which it's my favorite term, which is times v over dx of the baby function, g of x. Now, these things that's we need, Jay and Caitlin, to maybe half of the course is going to be relied on this one, and also the rest of your career in math is going to be also relied on these two ones. Now, these are the things that we cover. Now, what I'm going to do is that I'm going to use these two things plus these things to find what is the rate of change of the logarithmic function of a tangent function when the x changes over. Essentially, what do I mean is that I'm going to find these things which I have right now. I say if this is f of x, I'm going to find this one. I say d over dx of f of x, as f of x is this, it's essentially d over dx of ln of tangent of the x. You say, okay, how ln tangent of the x is going to change when x is changing itself. Now, that's going to be the topic by using these two. First of all, before solving this, I'm going to add something to this before we use that chain rule. I love chain rule a lot, and I hope that also you love it. Now, I'm just going to add the third identity here. We are going to fill this together. And I'm going to say, what is d over dx? We talked about the sinus. We talked about the cosinus. And why I'm not talking about, let's say, the tangent of the x? What is this? We're going to fill this together. In order to find this, I'm just going to save this spot for this equation. I'm just going to write this one here. We say that we are starting to work with this. We say that you're looking for d over dx of tangent of the x. In order to solve this, you say, okay, I know what is d over dx. That's the operator, that's the hammer, which is going to smash this function over here. Then I have no problem with it. Then I continue writing it. However, you know from one identity that we learned a decade ago that we said that the tangent of x or any variable is the ratio of the sine of that variable over the cosine of that variable. Now, if that's going to be the case, I'm going to substitute for tangent of x of sine x over cosine x. Now, any questions so far? Everything's fine? Yes? Now, when I'm at this stage, I notice that I'm going to take a derivative of a function which is a kind of a rational expression. I have one thing on the top, one thing at the denominator, which both of them have the variable x. Then what to do, we learned before our summative test, we have two strategies to work it through. Let me see how far I can go that way, that I can be on the camera still. All the way probably to here. Let me put the boundary on this. The first method, method number one. The first method is that I say, okay, I'm going to write this like this, d over dx of sine x, which is multiplied to cosine x. When cosine x comes up, you know that we have to give it 1 minus as an exponent. Yes? Look at this. You have 1 over a. You want to bring a upstairs. Then you say, okay, no problem. I bring you upstairs, but I'm going to give you a tag. And that tag is exponent of minus 1. I'm going to do the same thing here. And I say cosine minus 1 of x. You know, the minus 1 goes for the cosine. Okay. Now, when you are there, you say, now, I have a product of two functions. Guys, I don't like the way which I did it. I think I have to use the chain rule now. Let me just go to the second method. This one, second, let me erase this. Come to start first by doing something easier, then come back to this. I'm just going to leave it there. I'm going now to just right away solve it from the second method. This one I'm doing a little later because this one involves the chain rule. I don't want to just do this one, I'm just going to do it easier. You see that the d over dx of tangent, let me write it here. That's an actual expression. Here is, yeah, let me just write it. I just put step number 2. It's the quotient law. It says that, if you remember, we said that d over dx of a function which is f of x over g of x is what? D over dx of f g minus f d over dx of g to the power 2. Remember that. I'm going to do the same thing. If I do this, I say the derivative of the cosine, look at this one. I have the derivative of the sine times cosine. How much is the derivative of the sine? Cosine. Cosine times cosine, how much is that? Cosine is squared. Minus the derivative of cosine times sine. I'm just not doing anything except I'm following that quotient law that you learned. The derivative of the cosine becomes how much? Minus sine. There it is. That's what you have. It becomes minus sine. Times sine becomes how much? Minus sine squared, huh? Over the denominator goes to the power 2, which it takes it to be cosine squared of x. Now, you say, the first thing which comes to my mind is that I have one minus sign there, and it acts on the minus inside the parenthesis, and it gives me this very easy expression, cosine squared of x plus sine squared of x. Yes, I'm right at that point. And now, we have also the denominator, cosine squared of x. Now look at this. What does it remind you? The one at the very top. Yes, please. That's right. Thank you. Look at this one. The one at the denominator is the first that we have made that is always with you. The cosine, and that's this expression. Sine squared of x plus cosine squared of x, it is always 1. Pythagorean theorem, as McDougall said. Yes, Amr? Yes. Now, this is always valid. Then if I have j here, cosine squared of x plus sine squared of the x, then Brooke, how much is that going to be? This one, cosine squared of x plus sine squared of x becomes 1. Huh? Then as a result, I have 1 at the top, and I have cosine squared of x at the bottom. Easy so far, huh? We can stop there. We say, I've done 1 over cosine squared of the x is going to be the answer. Or you say, no, I'm curious because I know that from the things which I learned in the past, I know that 1 over cosine of x is another trigonometric identity ratio, not identity ratio, which is secant of x. Have you seen that before, huh? Advanced function course. Yes, everyone? The secant. Then you see that if because 1 over cosine, it's a ratio, it's inverse of the cosine ratio, it has a different name. They call that secant of the x. Then you say, wait a minute, 1 over cosine squared of the x is going to be secant squared of the x. And now we are done. Then, as a result, I come over here and I say derivative of tangent of the x becomes secant squared of the x. That's how we got the third identity. I didn't use anything except I used the knowledge of the first two and the quotient law. I got to that. Yes, Matuna? How beautiful is that? Yeah? Yes. Now the first one is going to be very interesting. Give me 30 seconds. Actually, the first one, I'm just going to ask you to do that. Not you, everyone else. That I do that on the board. Because this one, the second method is going to be, not the first one, but the second method was this. Any questions on the first method? The quotient law. Any questions? How did I get to this one? Everyone is fine? If you are fine, just please come here, complete what I wrote for the first method. For the first method, I said that the tangent is sine over cosine. I said that I can just bring cosine upstairs by adding it, by giving an exponent as -1. Now, I have two functions, the product of two functions, Sebastian, and that's sine x, cosine inverse, cosine not inverse, cosine -1x. Then as a result, now, what we are going to do is that use the product rule to find the derivatives. Please you do that to see how far we can go. I'm going to write the law which you need. I'm just going to write it here. That was a quotient law. The product law is this: p over dx of f of x g of x. It becomes g of x plus f of x p over dx of g of x. And also, you may need to know this one, that d over dx of or maybe if you are more interested, you can use this one. I love this one. The last one sounds so neat. Yeah. How's everything doing? You know? Need the last one, the one which I wrote over there, or? The very last one at the bottom, we have four rules. We have four. This is the quotient law, that's the product law, that's the power law. The last one, my favorite, is the combination of the power law and the chain rule. This is still the power, you know, the exponent power. If you compare the third and the fourth one, They are so similar. Yes. That's so true. Good for us guys. We have a lot of time for calculus. You're done? Yes, please. Now, I'm just going to do that. Just please help me as we move along. Yes, Sarah? Yes, you're fine? Awesome. Now, guys, look at this. Now, I'm just going to do the second one. I need some instructions. Those instructions are given. I need these three ones. Why do I need the first one? The second identity, the product rule. I need it once because I see that the sine x and cosine to the power minus 1x, it's not cosine inverse, it's cosine to the power minus 1x. There are two independent functions that they are multiplied with each other, and that's the reason I need this one first. If that's the case, I'm going to write. I'm just going to write as the way like this. I say that. It becomes the derivative. It becomes cosine to the power minus 1 of x. Fancy. D over dx of sine x, which it means that the derivative of the first one times the second one. However, plus the derivative of the second function times the first one. It means that sine x over times d over dx of cosine to the power minus 1 of x. You see, that's the kind of the beauty of the calculus is that you do not need to think much. You just have to follow step by step, and everything shows itself. This is not like the geometry that you have to think of in 4 dimensions. Now everything comes by itself. I used the second identity, the product rule J, and I got this one. Now, when I look at this, I see that I have one term, because cosine to the power minus 1x is easy. I have d over dx of sine x. Look at this. D over dx of sine x is cosine x. Then what do? I write it the way it is. It becomes cosine to the power minus 1x times cosine of x. So far, so good, everyone? Plus, I have sine x, which is multiplied to the derivative of cosine inverse of x. Why I say that like this? Because look at that. The fourth identity, which is here, that's what I need for the second operation. It's like the power rule. It says that. It's essentially, you can prove this one using the chain law, but I'm just going to use it right now. If that's the case, I know that the derivative of this expression becomes what? Look at this expression. Power minus 1. Power minus 1. Yes?
Isn't it the derivative of theta?
If we go that way, we have to just go for another identity of the x of the theta. Then I'm not going to drive this, I'm just going to simply use that. Also, that's correct, you can do that. You can also, if you get some time, Sebastian, we can introduce another identity for the derivative of the theta. But now we do not have that identity. Let's move on to the laws that we already have. Here becomes sine of x The minus 1 imagine like the power rule. Then becomes, I take minus 1, comes outside, then it becomes, look at the fourth law over there, the power rule, resulting from the chain law. N times f of x to the power n minus 1, my f of x is what? Cosine x minus 1 becomes how much? Minus 2 times the derivative of the pure function itself. Let me go. Now, look at this one. The derivative of, if you look at that, this is exactly fourth law, is an extension to the power rule. Then becomes the derivative of d over dx of the pure function itself. What is a pure function f of x? Cosine x. Now, you see, I took one more step. Knowing all the things that I needed to know, all these things get this from a couple of sessions before. Now, we come to, yes. Any questions?
Where did the
Yes.
second view of the x?
One.
Where
Look at this one. You can
always
prove,
the
that's right. You can use the chain law, but you remember a couple of sessions ago, we said that we have this one power rule. It was the first one we learned. Then we said that if I have f of x, which it comes with the power, I can extend this one to this. I take the power, comes fall from this one. Instead of x to the power n minus 1, I write f of x to the power minus 1. Then I set d of the f of x without the power. Then it cosine to the power minus 1. If n is minus 1, the f of x is cosine x. Then the last term d of x is cosine x, d over dx of f of x becomes d over dx of cosine x. You got it?
Yeah.
It's clear for everyone? Yes? Everyone is happy? Happy. Yes? Now, I go to the next step. The next step is going to be even more fun. Look at this. I have cosine to the power minus 1x, which is 1 over cosine x, times cosine x. How much is that? 1. It's 2 inverse 1. You multiply this. It becomes 1. Plus, I have this one. Minus 1 plus. Look at this one. What is going to be inside this? Plus sine x. I have minus 1 times cosine to the power minus 2x. You do not need this one, it's a good practice. Because the first method, the second method was enough. Times the derivative of cosine x. The derivative of cosine x is given here, minus sine x. Then you see, it becomes times minus sine x. Now, then at the end, you multiply everything. It becomes 1. Sorry guys, if it's too loud, just so sorry. I guess if I could just pull it off. It becomes 1 plus. What do we have inside? We have minus cosine to the power minus 2x minus sine x. Your sine x is multiplied with this. Then this minus and this minus becomes plus. Then you have sine squared of x times cosine to the power minus 2 of x. I need more space, probably I guess. Any questions so far? No? So far what we did, we just got the 1 over here, and we have sine x. We have minus cosine to the power minus 2x, minus sine x, these two become plus cosine squared of the x, cosine the power minus. Now, I'm going to take this one, bracket a little bit here. Let me just use a different color. I recommend you guys, yes, please. I recommend you also you do this practice at home because it's very good practice for you to just see how to use different rules. I'm going to take this one here, which is 1 plus sine squared of x cosine minus 2x. Now, what is this? It's essentially like writing 1 plus cosine to the power minus 2. If you can bring it downstairs with the plus number, which becomes sine 2x over cosine 2x. So far, so good, everyone? Yeah. And we asked Maktuna, what is happening there? Oh my God, I lost my breath. So much work. Yes, Don, what's going on there? It's crazy. It's insane. Now, I say, Don, no worries. Because you see, the last part is going to be very easy. I'm going to write it in red. And you see that how things are easy in calculus. Everyone look at the board. I'm going to prove it to you. Calculus is the easiest part of the math I've ever seen and you will ever see in your life. Look at this one. So far, we have this expression. I know the row that the result from the method number 2, the derivative of the tangent has to be secant squared of x. But I'm so far away from this. Look at these crazy lines. But all the way up to here, I say, okay, let me take the common denominator. What is the common denominator between 1 and sine squared x plus over cosine squared of x? That's right, cosine squared of x. Then the first term, you are doing the social justice. You say that the denominator is multiplied with the cosine squared by multiplying numerator. Then you have cosine squared of x. And you have also the sine squared of x remains there. Now, look at this. So again, we got to the same. Sine squared plus cosine becomes how much? It becomes 1. We have cosine squared of x. Oh my God, look at this, we got there. Oh my good Lord. Look at this, we got again to the 1 cosine squared, which is again the secant squared of x. I recommend you very much that you do the same thing at home, follow step by step, because it's going to be an incredible important practice for you. Especially you have one method, you reconcile the other method to get to the solution. You see, everything was easy. Just common denominator, Gabriel, and prove this. Now, how much time do we have? Half an hour? Yeah. If we have half an hour, before we continue, if you have no questions, or if you have a question, I'm just going to give you 1 minute break to just, to recover from that thing. Then we continue with the other problem. So many more words. Guys, before, which one was mine? Guys, before I do solve this one for you today, which I'm going to do that by 1:15. The class is by 1:25, huh? Yeah. Yes. Now, before that, in order to do some practice, specifically as John asked how to do this one, I'm just going to give one more practice with the tangent functions, but we are going to use that chain rule there. Then you spend a couple of minutes to think of it before we solve it. We said that find p over the x of this function. Let's do this. Let's go crazy. Okay, now, we are just going to solve this. However, we know that we have only one identity. We have covered it today. And we said today, we derived it essentially there. Still, this is there. We said that d over dx of tangent of x is secant squared of x. That's the thing that we drove it. Now, I said that, wait a minute, I know that the derivative, rate of change of the tangent of a variable, when that variable changes, it becomes secant squared of the same variable. Then I give it a problem like this. I say, look at this. Let me erase this one. Let's color code it. And I say the d over dx of tangent of the sine x. I say, oh, look at that. I'm looking for the rate of change of the tangent of the sine of the x with respect to the changes of the x. But I cannot use this equation here because it says that the tangent of x with respect to the change of the x becomes secant squared of x. Now we have tangent of sinus of the x. Then you see that if I write it in red, you see that I have sine x in front of the tangent, which I'm looking for the derivative with respect to the x. Then that formula is not a very good one. Yes, everyone? Yes, Caitlin? Yes? Now, the thing is that I want to give you 2 minutes. I'm just going to use the chain rule. 2 minutes to try to see if you can solve it. Then, after 2 minutes, I jump in and we do it together. Guys, help me to solve it then. Now, guys, look at this. The same family, a mother is a pregnant baby. The mother function, what is the mother function? No, this rule is the Bible of the calculus. Guys, everyone please. Look at this. The mother function, if you look at the function, look at this. Let me write it like that. F of x is the function which is inside. Now, look at this one. This is still the same scenario. A mother with a baby inside. The mother function, Tommy, is tangent of the x, and let me introduce the baby to you. This is sine of the x. Now, we want to find the derivative. What did I say to you do? You say, you step back, you look, you point to the baby, say, hey, you. That's how you solve it. You look at, hey, you, and like that, as easy as that. What does it mean? It means that you take the baby, you call it you. There was a purpose that I said, you say, hey, you. And that's why, because you call the baby you. Now, look at this. Then if you do this, what happens? You say that. Then as a result, the f of x for you changes as the tangent of u. Instead of the baby, I call him you. Then what happens if I look at this part? This part is very crucial. The thing which I'm going to do right now, it's the explanation in details done and Sebastian why I said this rule works. This is the explanation how from here you can memorize this. Now, I say that I'm looking for d over dx. There is no question. I say that I'm looking for d of f of x with respect to the changes of the x. Now, Dave, I say in order to do this, I'm just going to connect two chains. That's why it's called the chain rule. You are connecting two chains. The first one and the second one. The first one is this. I said that the first one is d of f of x. I also, remember, I have d of x. And at the same time, what do we have? Someone is behind the door? Or no? It's not a shadow. And now, look at this. We have d of f of x over dx. Now, if I put du over here, changes of the baby, you see that nothing has changed. Because these red signs, these red derivatives, because they are multiplied, they cancel out. And at the end, when they cancel out, then d of f of x with d of x, they join, they become the same thing. But it was a smart trick to separate them by chain, introduce these du in order to solve this problem. What is d of f of x with respect to the u? Let me call that d of f. Look at this. What is f there? You can call it also u, because if the x, you change it to the u. It doesn't matter at all. Just look at this one. What is d of f with respect to the changes of the u? Huh? You have, it becomes like that. It becomes d over du of tangent u times, what is d of x of u? That means that d over dx. And for the u, remember, we just pointed at the u. We said the baby is u. That's the sign of u. So far, so good, everyone? Yes, who said that? Let me explain more. What is wrong?
I don't understand the du. Oh, du, okay.
This one or this one?
So du is d of sine of x.
U is the sine x. When we haven't worked to see what is du, we haven't done it yet. We know u is the baby sine x, but I just use this operator. I haven't yet worked through this. Yes, Dave. Yes, okay. Absolutely, please. Now, at this stage, look at this one. Quickly, what's happening here? I have tangent u changes with respect to the u. What is that? I look at this, I say u over dx of tangent is secant squared of dx. As long as x and the x are the same, I know that the changes in group. Tangent is squared of x, yes? Then as a result, the first expression becomes what? Becomes secant squared of u. Just because of this identity, we draw it over there, and that was the proof. And now, Sebastian, now that what we are looking for, the du, look at this, and now, d of sine x with respect to dx, how much is that? I erased it. We learned it last week. D over dx of sine x becomes cosine x, correct? I'm going to write cosine x. Now, then as a result, I'm just going to write it here. Then as a result, what do I say? I'm just going to write it just right here and continue here. Look at this. I have. Then, let me. How can I write it that you do not get confused? If I. Let me write it there. I continue here. Is it okay, everyone? I continue here. Nothing confused. Then I say that d over. What was the original problem? The original problem was this. D over dx of tangent of sine x. Then when I called the sine x u as a baby, and I made that a smart trick, I ended up to this. Secant the square of u times cosine of x. Now, you say, oh, wait a minute. I have here x, I have here sine x. Then what the u is doing there? wasn't that the baby that it was sine x? This one here? I say yes, let's bring back the baby. Let's not call it u. Then it becomes what? Secant squared of u is going to be the sine times cosine of x. And now we are done. Ah, I love it. Any questions? You say, oh, what am I talking about? Oh, why do you want it? Yes? What's too wrong about that thing? Now, yes, Sebastian.
I just don't understand when you went from d of f over du and d over
You
dx.
go to this one?
Yeah, I don't understand how you went to this step overall.
Yes. Are you finding so far that we said that the problem is this, to find d of f over dx? You're okay? Yeah. That's all we are here to do, that, to find d of the function with respect to dx. But because there was a baby and we called it u, I made this a small trick. Look at this, Sebastian. D of f and d of x is there. And I bring these two, I should say, operators, that one is on the top, one is at the base. Yeah. It means that when you multiply them, these two cancel out, and you have again d of f over dx, the same thing. Right. But doing that a small trick, it helped me to say that d of f is d of u, because I know that because the baby is u, it becomes very easy to find it. And the derivative of the baby is given, which it means that this expression, Sebastian, tells you that when you have a composite function, the rate of change becomes the rate of the change with respect to the parent functions times the rate of change of the baby function. And that's the reason that I did this. And you see that when you do this, the calculation becomes very straightforward. Because d of f with respect to the u, you have d of tangent u over u, you learn it becomes secant squared of u. D of sine x, the baby, of the x becomes cosine x. Then the rest of it, you substitute u for what you had there. Make sense? Yeah. Awesome. Now, I'm just going to connect that one to this rule, which I said to John, this is a kind of a Bible in the calculus. How much time did we have? 10 minutes. Very well. Yes. I did a great job today. I'm really on time. Now, look at this. I'm going to do the same thing here, the same function. I'm not going to do this rule, the chain. I'm just going to use this formula to ease guess them. Yes, please. I have d over dx of tangent of sine x. Now, when you want to find this, you say, one way is this. One way is this very beautiful, detailed calculation. Yes, Cyrus? But sometimes you say, oh, as Sebastian says, I can see here in his eyes, I don't like this one. This one, I just want to use the Bible to find it. The Bible, the calculus, I mean. Don't take me wrong. Now, then what you say, look at this one. We have f of g of x. My g of x is g, my g of x is sine, and f of x is tangent. I say d of f g of x respect to g of x. The same thing that we do. It becomes, imagine this has become tangent of the x with respect to the tangent of the x, but at the end you put back the baby inside. The tangent of sine x with respect to the sine x, that's what it means. D over d of sine x times tangent of sine x. That what does it mean? F of g of x, that's tangent of sine x. But d over d of g of x. My g of x is sin x.